My name is Brett Belcher, and today I'm going to be presenting the paper See, Hear, and Read Deep Aligned Representations, authored by Yusuf Aitar, Carl Vondrick, and Antonio Torralba. I just want to point out that we have actually seen a paper already written by Yusuf just about 2 weeks ago, presented by Chris. That was the Exploiting Convolutional Filters. He wrote that 2 months after this, and you'll see how transfer learning comes up in this previous work as well. So I'm going to start off with an overview of what I'm going to be talking about in my presentation. First, I'm going to talk about cross-modal representation, its motivations, and all of that. Then I'm going to move on to describing the data sets that they used in this research. I'll talk about a little bit of background on the techniques that they used to perform these experiments. Then I'll discuss their network architecture and the implementations that they used. And then finally, I'll go into their experiments and the results they got from those experiments. So first, cross-modal representation. The point of cross-modal representation is aligning representation across modalities. In this research, the authors use sound, vision, and text. The idea is to get a representation invariant of the modality of the input you put into an architecture. So in this, they wanted to align the representations of sound, which they inputted as spectrographs, vision, which were images or just frames from videos, images, and language, which were sentences describing the images that they used. It's important to note that to align representations across modalities, we're going to need paired data, and I'll go into that when I talk about the data sets that they used. So, their data sets. They used sound image pairs and text image pairs. It's important to note that they did not use sound or text pairs when they were training the network. They did, however, test how good it was at aligning just sound to text, and I'll describe that when I get to the results of their experiment. So the sound image pairs that they used sound from videos that they got off of the website Flickr and the corresponding video frames to those videos. And for the text to image pairs, they used a combination of the COCO dataset and the visual genome dataset, which the text in those are descriptions of the images in the data sets. So, first I'll talk about the sound. They used the extracted spectrogram of the videos that they got off of the website Flickr, and the only pre-processing that they performed was a mean subtraction. Let me actually get this pulled up. I will need that for later. So the only pre-processing that they performed on the spectrogram was a mean subtraction, and they used approximately 5 seconds of audio from each video that they got. What they did was they used 85% of the audio for training, and the rest of it was used for testing. And again, they used spectrographs, which can be visualized in this way. Now the text that they used the COCO and visual genome image descriptions dataset. The training and testing splits were kept the same as they come from the COCO and visual genome datasets, and duplicates between the datasets were removed to reduce redundancy. The pre-processing that they performed was a removal of English stop words from the text, and they embedded each word as a Word2Vec, so they could put it into the network as a one-dimensional vector. And again, they used simple descriptions of an image, such as a train in the shape of a boat driving past a road. The COCO and visual genome datasets are quite large. The COCO dataset has about 400,000 sentences with 80,000 corresponding images, and the visual genome dataset is much larger with about 4.2 million sentences corresponding to 100,000 different images, or sentences with 100,000 corresponding images. The vision or images that they use in the data sets, which again, this was the bridge between all of our modalities. They used the frames from the sound dataset and the images from the text description datasets. And the pre-processing that they performed on this was subtraction of the channel-wise mean of the RGB values. And the training and testing splits were kept the same as the sound and the text datasets. So they didn't change any of that. And again, the vision can be seen just as the images that they used. So now that we've gone over the data sets that they used, I'm going to go a bit into the background of the techniques that they used to perform their experiments. First being alignment by model transfer, which is just a different name for transfer learning. We've gone over this a decent amount so far this semester, reading a lot of papers on transfer learning. So since the images were our bridge modality, we used a trained image model, or trained discriminative visual model, to teach the student model in this research. So they used the ImageNet model for training, and then they used the KL divergence between the ImageNet model. Here they represent the ImageNet model as the function g and the output of theirs as the function f, and they attempt to minimize the KL divergence between the two. And KL divergence can be seen as the log difference between the outputs. Now, alignment by ranking is the other technique that they use in this research, which is a different name for contrastive loss or triplet loss. I'm sure we're all familiar with that now after all the stuff we've done on it. So I think we're all decently familiar with this maximization function, but I'll go over it real quickly. We're attempting to push negative samples away in our embedding space while pulling positive samples closer together in our embedding space by this margin delta. We can see that we're subtracting the psi similarity function, which I'll get to in a moment, where we're iterating through all of our samples I, and our negative samples are j, where I does not equal j. So we're subtracting the similarity between our positive samples while adding the similarity between our negative samples, the anchor and its negative. And the psi that they used in this was a cosine similarity. So we're using the cosine similarity to measure how similar the positive is to the anchor and the negative is to the anchor. Now I'm going to go ahead and discuss the network architecture that they used to perform this. This is split into three different parts of an architecture, so I'll go one by one. First, I'm going to start off with their image architecture. All of these architectures start off with just 4 layers. For the images, they use the ImageNet model from 2012, written by, I believe his name is Krzyzewski. They used it up to the 4th pooling layer, and after the 4th pooling layer, they go on to 2 layers that are fully connected of size 4096. And this is where we get our teacher loss that is backpropagated to throughout the image model. The sound comes in as two-dimensional as it is represented as a spectrograph, and they perform one-dimensional convolutions on it, again for 4 layers of one-dimensional convolution before coming up to these 2 shared layers of size 4096 that are fully connected, and this is where our paired loss or our contrastive loss comes into play across these shared layers. And the same goes for the text. The teacher loss is propagated through to get the modality specific representations, and the shared aligned representations come up before the final output representation, final representation is outputted. Now I'll quickly go over the implementation that they did to perform this. They used mini-batch stochastic gradient descent and backpropagation. They used an atom solver with a learning rate of 0.0001. They initialized their parameters with Gaussian white noise, so they started entirely from scratch, except for obviously the ImageNet model they used for the transfer learning. They did this with a batch size of 200, and they went over 50,000 training iterations, and this training took approximately 1 day when they trained it on a GPU. And now I can go on to the results that they gained from these experiments. So they tested this on cross-modal retrieval, which means given a query in one modality, how well can we retrieve a corresponding pair in a different modality? So if we have an input query, which is if we say it's just a picture of a dog, what can we retrieve from that? Well, this network could retrieve sounds that correspond in the same representation to a dog. In fact, they show the original video clipping over the spectrogram of the sound retrievals, which you can see that dogs do come up in this, and they give a quick text description. It's just the sounds of barking. With the input query being a dog, we can get text retrievals that also relate to this representation. And we can get image retrievals related to this representation. And the same thing goes if we change the modality of the input query. If we change it to, say, a spectrogram or a sound of a train engine, we can get retrievals in any modality about the same representation. And the same if we have the input query as text. So how well did these actually perform is the question. So they tested it with a limited amount of baselines. They used random, linear regression, CCA, and normalized CCA to test it. And starting out with how well, if we input an image, it could retrieve sound. This was done on the average median rank of 5 tests of 1,000. So random gives us a score of 500. We're looking for a lower number. So linear regression would get lower, CCA and normalized CCA could perform better, but even just using the transfer learning, we could see better results than a normalized CCA. If we use the triplet loss, we can also see even better results, and by using both model transfer and ranking, we achieve the best results. And if we do sound as our input query to an image retrieval, we can also see this same pattern emerge. They actually don't give a description on why ranking alone did better than using both in these results. But as we can see on all the other experiments, using both performed better. So if we have an input query and we're trying to retrieve text, we get very good results using both. And if we input text and attempt to retrieve an image, we still get good results. But this is doing with an input query of image and an output of sound, which we trained the network on image sound pairs, and we also trained it on image text pairs, but we didn't train the network on sound and text pairs. So how well could it do with that? And they tested this. They couldn't use CCA as a baseline for this, but they could still use random and linear regression as a baseline. So with the input query being text and they were trying to retrieve sound, how well could it do? Well, we can see that using both model transfer and ranking, we still achieve better results. Now, these aren't nearly as good as the pairs that we did give it training data for, but we can see that this was starting to learn good representations between these modalities. And the same thing vice versa with the input query being sound and the output query being text. We can see that both using model transfer and ranking yields best results. And now lastly, they describe something that they call hidden unit visualization, which is what they did was they visualized a few units from the last layer of their cross-modal network. And they wanted to see if any nodes specifically became most active when certain representations were giving in. And they did see these results. They would see that these final activations would become very high when anything related to, say, a pool was given or anything related to a sports fan was given. These nodes would become most active, and they could see these start to come about. And the same thing comes out with anything water-like. You can see that all of these input queries, say any of these images or these sentences, would yield high activations. Same with dog-like, and same with sports-like or wind-like. These all made these final units most active.